So in this video, we're going to look at the idea of resolving forces, or you sometimes see it's called the resolution of forces. So I'm going to talk you through what that means and how we use that to split up a force into two, what we call components. So I'm sure you're all familiar probably with the idea of riding a bike. If we're riding a bike along a nice flat surface, then it's fairly easy for us to ride a bike, and that makes sense. But if we change the situation up a bit and instead we're riding up a hill or up some kind of slope, then I'm sure you're familiar with the fact that that doesn't feel quite so easy and it's more tiring. So we could explain that in terms of energy. We could say that we're having to convert more chemical potential energy from the food that we've consumed into gravitational potential energy in order to move up the slope. And that's one way of looking at the situation. But actually, if we look at it in terms of the forces that are present, it's quite easy to see why it's the case that cycling up a hill is actually trickier. So let's have a look at the forces that are present in this situation. So we're going to ignore friction and air resistance and things like that for now. So really the only force we're bothered about here is weight. So we know that weight as a force always acts vertically downwards. So we're going to say that this person and the bike have a combined weight and they act from the centre of mass. Let's just say that's this point here, and they act vertically downwards, like so. So that's the weight, but hopefully we can see that there's a downwards or a downhill component to that weight, and that's why it's so tricky to cycle uphill, because there's part of the weight that's acting against the direction that we're trying to move in. So if I kind of draw that on to show you, there's a component of the weight that acts down the slope against our direction of motion, like that, and then there's another component of the weight that actually acts perpendicular or at right angles to the direction of motion or to the direction of the slope. So that's this component here. So we can see that completes a right angle triangle. So we've got the weight acting vertically downwards, we've got a component of the weight that acts parallel to the slope, and we've got a component of the weight that acts perpendicular to the slope or at right angles. So that's the idea of the resolution of forces. We take one force, so in this situation that was the weight, and we split it up into two components that are at right angles to one another. So before we go any further and look at a few more examples, it's important that we understand some of the language that's going on here. So it's very important, two words here that are very important to understand. The first of those is the term parallel. So hopefully you'll have seen that in maths. But if something is parallel to something else, so you could have parallel lines, they look like that. So they aren't at an angle to each other. So if you were to continue these lines on forever, they would never meet. Okay, so they aren't at an angle to each other, they're just parallel. So that's why with the cyclist, this component here was parallel to the slope. You can see that this is the line of the slope, this is the line of that force, and they would never meet because they're not at an angle to each other. They are parallel. The other word that I mentioned was perpendicular. Okay, and that's just a fancy way of saying at right angles to. So here's one line. A line that would be perpendicular to it would look like that. And they have a right angle between them. In other words, they have 90 degrees between them. So this component we said was perpendicular to the slope. And you can see how that's the case because here's the line of the slope. and that is clearly at 90 degrees to the line of the slope. So it's important that we understand those terms, parallel and perpendicular. Okay, so let's have another look in a bit more detail at another example of this. So quite often in these situations, you'll be faced with an object on a slope, just like what we looked at with the cyclist. So sometimes this is called a slope, sometimes it's called an inclined plane, but both of those terms mean the same thing. It just means that you've got some kind of surface which is inclined at some angle to the horizontal. Okay, so in this situation, we have a slope that's inclined at 30 degrees to the horizontal, like so. And here we've got a box sitting on the slope, and that box has a weight of 50 newtons. So again, the weight we know acts vertically downwards towards the centre of the earth in every situation. But there is a component of the weight that acts parallel to the slope or down the slope, and there is a component of that weight that acts perpendicular to the slope or at right angles to the slope. And we want to be able to split up that force into those two components. So the way in which we do that is, first of all, we take a ruler and we line that up so it's perpendicular or at right angles to the slope, and so that it matches with the point from which the weight is acting. And all I'm going to do is I'm going to draw a line. I'm going to draw a dotted line so it's a bit more distinguished from the other lines. And we just draw a line along where we've placed the ruler there. So that is a line that is perpendicular to the slope. Now the next thing we're going to do is we're going to take a ruler again, and then we're going to place it so that it is perpendicular to the line that we just drew, so at 90 degrees to the line we drew, and so that it matches up with the end of the force arrow that represents the weight. And we're just going to draw another line along where we've placed the ruler, like so. Now to find the actual components, all we need to do is complete this right angle triangle here along the lines that we've just drawn. So this line here represents the component of the weight that acts down the slope or parallel to the slope, and this component up here from the point where the weight acts down to the line that we've just drawn is the component of the weight that acts perpendicular to the slope or at right angles to the slope. So in blue there, you can see how I've taken the weight, this red arrow, and I've split it up into two components that are at right angles to each other. One that's perpendicular to the slope and one that's parallel to the slope. And this is useful because it can help us understand what would happen to objects in situations like this where they're on a slope. So for example, if we know this component of the weight, we know how much friction is required acting up the slope in order to keep the box in place. And if it happens that this component of the weight is bigger than the friction, so let's say we represent the friction just with a little arrow like this, which we can see is smaller than this component, then we know in this situation that the box is going to slide and accelerate down the slope because this force that acts parallel to the slope is bigger than the friction. So that's why it's useful for us to be able to split up one force into two in situations like this. Okay, so we're going to look at an example now which is slightly different. So instead of having an object on a slope, we could have a situation like this. So here we've got a plane, and the red arrow, the dotted red arrow, shows us the direction of motion of the plane. But At an angle to the direction of motion, we have a force due to the wind, and it's at an angle of 30 degrees to the direction of motion, we can see there. And this force has a magnitude of 800 newtons. But it would be useful for us to be able to work out how much of that force acts against the direction of motion, because that could again tell us whether this plane will accelerate or decelerate or move at constant speed. So it's very important. So again, all we need to do is split up this force into two components that are at right angles to each other. So to do that, all we need to do really is draw a right angled triangle. So I'm going to line up my ruler so that it's perpendicular to the direction of motion, to that red arrow. And I'm just going to draw a line that matches up with the end of the force and that line that shows the direction of motion. Okay, and that is my component that acts, of the wind, that acts perpendicular to the direction of travel. So I can label that on with an arrow to show its direction. Now the other component is the one that acts parallel to the direction of motion, in other words, against the direction of motion, and it's this force here, in that direction. So there I've split up the wind into two perpendicular components, one that acts perpendicular to the plane's motion and one that acts parallel to the plane's motion. Okay, so one last example, and we'll look at this, this in a bit more detail, and we'll go through the full question. So here we've got a student pushing a trolley with a weight of 510 newtons up a slope that's inclined at 15 degrees to the horizontal. And what we need to do is determine the component of the weight that acts down the slope. So first thing I'm going to do here, I'm going to draw a horizontal line using a ruler, like so. And then I need to draw my slope. Now it doesn't really matter if you draw the slope up this way or up this way, either way is fine. It doesn't really matter, the question doesn't specify. So what we need to do is we need to use a protractor to measure out an angle of 15 degrees. Let's do it this way so you can see 15. So I'm going to line up my protractor with the end of the horizontal line I've just drawn, making sure it all lines up. And I'm going to measure out an angle of 15 degrees. So we can see that matches up with 15 on my scale. And all I'm going to do is put a little point there to show me the angle that I need to draw. Okay. And then it's just a simple case of joining up the corner of the horizontal with that point that we've just made. And then I know that I've got a slope that is inclined at 15 degrees to the horizontal. So I know this angle here is 15 degrees. Now the next thing, in a situation where we've got an actual question like this, is that we need to come up with a scale. Okay, and the scale is what allows us to actually work out the component that acts down the slope. So we've got a weight of 510 newtons. Just for the sake of ease here, I'm going to say that I'm going to represent that force with a 10 centimetre line. So 10 centimetres equals 510 newtons. So simplifying that really, my scale then is 1 centimetre equals 51 newtons. I've just divided those each by 10. So that's my scale. 1 centimetre equals 51 newtons. So next stage is to draw on my object. Now it's a free body diagram, so we just represent an object nice and simply, just like that. And the weight of that object is going to act from its centre of mass. And it's going to act vertically downwards. Now remember, our scale says that 510 newtons is represented by a line 10 centimetres long. So I need to draw a line vertically downwards that is 10 centimeters in length, like so. So there's the weight. Now remember, resolving forces means splitting one force up into two components. So in this situation, I need to split the weight up into a component that acts perpendicular to the slope and a component that acts parallel to the slope. So remember what we did? We took our ruler and we made sure that it lined up so that it was perpendicular to the slope and so that it met the point from which the weight was acting. So there is a line that is perpendicular to the slope. Next stage was to draw another line that's perpendicular to the one that we just drew and that matches up with the weight. So I'm just going to continue this a little bit so we can actually see a bit better when the line is perpendicular. So let's match up our ruler like so and make sure it matches up with the end of the weight, and then we can draw another line that is therefore parallel to the slope. If I keep the ruler like that and move it up, you can see that that line is parallel to the slope. So we're almost there. It's now just a case of actually marking on the forces and then working out what those forces are from our scale. So this part here is the component of the weight that acts perpendicular to the slope. And this part here is the component of the weight that acts parallel to the slope or down the slope. So from the question, we want the component that acts down the slope. So this is the part of the component of the force that we're interested in. So let's measure that line. So I can see from my ruler that that line is 2.3 centimeters in length. So all I need to do to work out the force that that represents is have a look at my scale and convert this length into a force. So to do that, I know that every centimeter equals 51 newtons. So 2.3 centimeters, I need to multiply it by 51 to convert it into a force. So on my calculator, 2.3 multiplied by 51, and that gives me an answer of 117.3 newtons. So that is the component of the weight that acts down the slope or parallel to the slope. And that is how we use the resolution of forces or resolving forces in order to split up one force into two components.